Hi friends, I'm going to talk about a very powerful transfer learning model, which is a artificial intelligence based model for doing the time series analysis and predictions. This presentation is based on the article published by Louis Rook in Towards Data Science. So what is TimeGPT? It was a foundation model for time series forecasting. It has been characterized by its ability to generalize across various domains. So it has the data this model has been trained on, in fact, almost 100 billion data points from different domains, including your weather, including healthcare, etc. And it is notable that there has been a lot of other contributions which have been made by a lot of other companies, like Carnegie Mellon University has published a similar model, which is Moment. Google has created its own model called Times FM. Morgan Stanley and ServiceNow has created its own model, which is Times FM. And Morai, which is a model created by Salesforce. So you find a lot of companies have done their own research, created their own models in time series forecasting, which are basically, as I mentioned, that these are transfer learning based models which have been trained on millions or billions of data sets and capture multiple sectors or multiple domains. This picture just gives a brief architecture of what this model is all about. So this is that is a Times GPT is a transformer based model specifically designed for some time series forecasting, incorporating a self-attention mechanism within an encoder architecture. By leveraging self-attention mechanism, it can dynamically weigh the significance of different points in the time series. So that's the biggest advantage what this model has, because the fact that it is the basic architecture which is utilized here is a transformer, that is encoder the decoder model. The model receives a window of historical values y and exogenous covariates x as input. The covariates may include additional time series data and or binary variables that denote specific inputs such as public holidays. These inputs are augmented with sequential information by integrating local positional embeddings. This allows the models to be aware of temporal dependencies, while it has not been explicitly stated as to which is the type used for position encoding, but we assume here that the cosine and sine encodings are being used to feed to the encoder. Now, as you can see from this slide, the encoder receives the vector resulting from the addition between the input and the positional encoding and generates a new vector to feed the decoder. Once augmented with position encodings, the input vector is introduced into the encoder. Now this positional encodings, we assume that these are sine or cosine functions because nothing has been specified as such by the author, but this is the assumption what we make here for the purpose of simplicity. Within the encoder, the multi-head attention layer evaluates and assigns weights to the various elements within the input sequence, reflecting their relative importance. Subsequently, this representation is processed by a fully connected feed-forward network. It allows the generation of a representation that captures more complex relationships between the elements in the sequence. The output is then fed to the decoder part of the architecture. Decoder receives an input, the output of the encoder, and previous predictions position encoded. In addition to processing the encoder's output, the decoder operates in an autoregressive process. It incorporates previously generated outputs before producing the forecast of the subsequent time step, that is I plus 1. It leverages the attention mechanism to capture the complex relationships between the hidden states produced by the encoder and the previously generated outputs. This approach enables the decoder to effectively synthesize the contextual and sequential information encapsulated in the encoder's representations with its own iterative predictions. A linear layer receives the output of the decoder as input and produces the final forecast with the same dimension as the forecast horizon. As you can see from the picture here clearly, finally the linear layer is responsible for mapping the decoder's output to a vector of values with the same length as the forecast horizon edge. TimeGPT can generate a probabilistic distribution of potential outcomes, that is, the estimation of forecast intervals. The author in this article has relied a lot on conformal prediction based on historical errors to estimate the forecast intervals. Unlike the traditional methods, a conformal prediction does not require distribution assumption, and it can achieved by creating M-training calibration sets, forecasting each calibration set with a model. With each forecast horizon edge, the absolute residual values between the model's predictions and actual outcomes within the calibration set are calculated. These calculated residuals are called non-conformity scores. We select a specific quantile from the out distribution of non-conformity scores for each forecast horizon edge. The chosen quantile determines the forecast interval's coverage level, with higher quantile resulting in broader interval. Lastly, we can see here the forecast intervals are given by the predicted value plus minus the final conformity score. Thank you very much.